So far, I've been giving you some really, really nice polynomials that are all nicely factored. But I want to look at this specific polynomial for a second. Take a look at this. It's the degree 4. Okay, we know it's going to be going up this way. We know it's going to be going up this way because, of course, degree 4s, everything either goes up or everything goes down. I know it goes up because this is positive, right? I even factored it out the best I could. I got up to here and here. So we know the real zeros for this guy is going to be 2 and -3. I'm just going to put those in right now. -3, 1, 2, 3, bada ba, and 1, 2. So we know at these 2 points, this guy should be coming down here, right, like this. This guy should be coming down here. They're all going to meet somewhere at -12, which is going to be way down here somehow. And then something's going to happen. Now, the something that's going to happen is this guy right here. What is up with that? Try to PSA that. You can't. There are no numbers that can multiply to 2 to add up to -1. It just doesn't work. So that's one of the reasons why I put it down here. It says solve this section using the quadratic formula. I want to show you what this looks like. Remember the quadratic formula? Minus b plus or minus a square root of b squared minus 4ac over 2a. And we said that this nice little thing underneath here is called a discriminant. And the discriminant determines whether the roots are real or not. Well, watch what happens when I plug this guy in. Remember, this is your a value here at 1. This is your b value here at -1. There's your c value at 2. Okay? So putting in our -1 plus or minus the square root of -1 squared minus 4 times a, which is 1, times c, which is 2, okay? Now, take a look at this, right? Over 2a, 2 times 1 is just 2. Watch this. This is really, really interesting. This gives us a -1, which is 1, plus or minus, okay, wait a second. -1 squared is 1, right? Minus 4 times 2 is -8. Well, wait a second. -8 plus 1 is square root of -7 over 2. You know and I know that that's an impossibility. You cannot take a square root of a negative number. That's why I say right here, they are non-real roots. Well, if they're non-real roots and the roots don't exist, that means this graph, although it's coming down this way and it goes through here, it's going to come up through this way and it goes through here at -3 and 2, which we determine were the roots here. How do we indicate a non-real root? I have no idea. So probably the best thing is, let's throw it on our calculator and take a look. So here's the equation all set to be graphed on my calculator. And if you look down here, I gave you the window settings. I want you to use these specific window settings. -8, 8, 1, -40, +20, 10 for the y, okay? So I've already punched that into my calculator. So let's go back to the calculator and let's hit graph. Huh? One of the strangest looking graphs I've ever seen. But there's our -3 as predicted. There's our 2 as predicted. Look how this graph wants to come up and it wants to do something here. Is it going to maybe round out and then go like this possibly? Maybe giving a multiplicity? Maybe, because this is, after all, a degree of 4, it wanted to do this, 2, and give you 1, 2, 3, 4 roots. But look what it does. The weirdest thing in the world. It actually just comes up like it wants to, and then it says, nah, I'm not going to do anything, and I'm just going to cut out through that way and go like that. Huh. So what does this mean? This little bend here is the thing that indicates that the roots are non-real. That indicates right there that the roots have to be non-real at that point. Okay, interesting. We're getting somewhere here. So going back to here now, you'll see that these roots are, in fact, according to that square root of a -7, non-real. Interesting, interesting. So let's keep talking here. I put a big note here. Very important to see. Now, it says if the polynomial function has non-real roots, remember the non-real root looks like this. And it's always a conjugate pair. Conjugate meaning that you have a plus or minus here. Interesting, interesting, interesting. And also under the bracket, this q value is got to be negative. Oh boy. Oh boy. Look at that. And as a matter of fact, that's what we did have. Look, there's our negative value. There's our conjugate, our plus or minus. Interesting, interesting. So let's make some conclusions here. Look at this particular graph. I got 4 examples here that I want to look at. And I want to start thinking about these things really, really carefully. Look at this. It says, first off, indicate the region that you think represents the non-real factors. Well, remember, we're looking for something that looks like it's going to bend towards the axis, but it doesn't, right? So look at this. Doesn't touch the axis right here. Think about this. This is like when we had those non-factorable polynomials last year in Math 20. You had something come down and not touch the axis, which you knew through the discriminant means that has to be non-real roots. Okay? Now, look at this. Okay, look at this. This does, in fact, have at least one root. So I would probably say that this is some sort of cubic polynomial, right? You have one real root, and of course, there's that conjugate of something really, really weird happening here. Look at this guy. Look, this has 2 roots, okay? And then some weirdness happening out here. So I bet you that's going to be a degree 4. Look at this one. This one has at least one real root here. And this has got some sort of conjugate there. Again, I bet you it's a degree 3. Last but not least, look at that. You got a multiplicity here. You got a root here. You got a root here. But you got that weirdness happening here again. See that weirdness? Right there. So I think you're probably going to have something strange happening there as well. Okay. So I've just indicated the places where I think they're going to be really, really strange. And I've got a pull tab here of my actual solutions. So I'm going to pull that over so that you can see my actual solutions. Okay. So let me get rid of the red marks that I had previously, and let's match them up. Let's see how you did. Well, yeah, see, just like I said, there's that real weird section right here. There's another weird section. There's another weird section, and there's the other weird section that I promised you was there. Okay, so my question then is, can we write a statement about this? What do you mean? I want to learn from this. I want to see, was I correct in my predictions? Was I correct in predicting the types and number and the multiplicity of my zeros? Okay, that's got to be cut through. So that's got to be at least one real root. Has to be at least one real root. That, of course, because it's a conjugate, right, and it doesn't touch it, that must mean that I have at least the conjugate, which, of course, is going to be my 2 non-real roots. See it? Because it's a conjugate, it's always going to be 2. Let's see if I can keep predicting now. Looking here. Okay, I said I have one root here, one root here. So I'm going to have 2 real roots. But most importantly, we forgot to talk about the multiplicity. Remember, this has got a multiplicity of 1. Okay, so same with this guy, because it just cuts right through. So this has got a multiplicity of 1 as well. Okay, now, what does this mean? That must mean the same thing. I have 2 non-real roots again. Interesting, 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 interesting. Okay, let's keep on going. Let's look at the third one. The third one says, yeah, let's go back up so we can see it actually. Look at that. I'm going to have one real root again, and then I'm going to have, again, a non-real root, multiplicity 2. Okay, so one real root, multiplicity of 1, right? I'm going to have 2 non-real roots because of that weird bend in the graph. Okay, cool, 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 cool. Okay, now let's look at the third one, which is really, really interesting. I like this one the most. Okay, check this out. That's got to be real root, real root, real root. So we're going to have 3 real roots, but one's going to have a multiplicity of 2. Okay, so we're going to have 2 real roots, actually 3 real roots. Okay, One has a multiplicity of 2 because of that bend, but it could be an even multiplicity. So it could be 2, it could be 4, it could be 6, dot, dot, dot. Okay? And the other 2 are just going to have multiplicity of 1. So the other 2 have a multiplicity of 1. Okay? What else is it going to have? It's going to have some sort of weirdness here. So again, because it's a conjugate, it's also going to have 2 non-real roots. Interesting. Well, let's compare my answers with the answer key that I have here. Okay, let's check it out. Uh-oh, can't really read this. So you know what I'm going to do? I'll just do that, and I'll bring it down here and compare. There we go. Like I said, the first one's going to have a real root, multiplicity of 1, 2 non-real roots. The next one, 2 real roots, both of them again, multiplicity of 1. Look, go back here. 2 real roots, 2 real roots. Here and here, multiplicity of 1 each, and then there's our 2 non-real roots, right? Boom, exactly. Look at the next one. One real root, multiplicity 1, 2 non-reals. That's for graph number 3. Okay, let's look at graph number 3. Sure enough, there it is. And this funky stuff that happens here. Interesting. Let's keep on going. Okay, our last one. Remember this one? We said we had 3 real roots. 2 of them have a multiplicity of 1. One of them has to have an even multiplicity, and we said that. Oh, look at that, 2, 4, 6, because it has a bend in it that looks like that. And then, of course, there's that weirdness in the graph that gives us our 2 non-real roots. An incredible part of what you need to know and how to graph this thing. Very, very cool.